Assalamu alaikum. Now, today we will have another lecture. We will have a little complex problem today. We are going to solve this problem with the help of direct method. We use infinite element analysis. So this is called the direct method, which we use infinite element analysis. For example, here we have a problem, a beam which is fixed from the upper end, and of a force P is applied on it on the lower end. So what we will do in this problem, this is called the direct method of FEA, direct method in FEA, finite element analysis. In this method, what we do is we divide the problem into a finite number of elements. In this problem, for example, we divide it into four equal elements of equal length, actually, right? So let it be L1 and L2. L1 is equal to L2 is equal to L3, and that is equal to L4. A force of P is applied. So this is element number 1, element number 2, element number 3, and element number 4. As I told you, it's a one-dimensional problem, so these will be the nodes which will have a deformation only in one direction. So let it be node 1, node 2, node 3, node 4, and node 5. So we have divided this problem into 4 elements and 5 nodes. Right, so we will solve it one by one. Each node, we will solve each node one by one. So for example, on node number 1 we have the two forces. One is the upward force of friction R1, and second is the downward force which the element number 1 is applying on it, right? Then we have element number 2, which have the two forces. Element number 1 is applying a force F1 on it in the upward direction, and element number 3 is applying, element number 2 is applying force. We're talking about this node, right? A force of F2 on it downward. Now if we talk about F3, node number 3, on node number 3, element number 2 is applying a force on it in upward direction, and element number 3 is applying a force on it on downward direction. Now if we talk about node number 4, on node number 4 we have element number 3 which is applying force on it in upward direction, and element number 4 that is applying a force on it in downward direction. Then we have node number 5. On node number 5 we have element number 4 which is applying a force on it in the upward direction, and we have the downward action force P. So this is node number 5. So we will write the equations for each nodes one by one. So what are the equations of equilibrium? Sum of all the forces in y direction equals to 0. So that will be R1 minus F1 equals to 0. And we know that F1 is equal to K1 into U2 minus U1, K1 delta U. So this is for element number 1. So the force in the element 1 is F1 is equal to K1 U2 minus U1. Force in element 2 is F2 K3 minus K2. And force in element number 3 is F3 K4 minus K3. And force in element number 4 is F4 is equal to K4 into U4 minus U5 minus U4. Right? So we can write it R1 minus K1 to U delta U, that is U2 minus U1, is equal to 0. So this is the force applied on node 1 due to the element number 1. So ये पहली क्वेश्चन आ गई हमारे पास for node 1. For node number 1. Now for node 2, we have the equation F1 minus F2 equals to 0. So that will be K1 U2 minus U1 minus K2 U3 minus U2, right, is equal to 0. We can simplify it. That will be minus K1 U1 plus K1 plus K2 U2 minus K2 U3, right? So this is equation number 1, and here we have equation number 2 for node 2. Then we have for node number 3, we have the equation F2 minus F3 is equal to 0. So that will be K2 into U3 minus U2 minus K3 into U4 minus U3 is equal to 0. We can simplify it. Minus K2 U2 plus K2 plus K3 U3 minus K3 U4 is equal to 0. So this is equation number 3 for node number 3. We have node for node 4, we have F3 minus F4 is equal to 0. So that will be K3 into U, because we have F3 in for element number 3, so that is between node 4 and node 3. So U4 minus U3 minus K4 into U5 minus U4 is equal to 0. We can simplify it. Minus K3 U3 plus K3 plus K4 U4 minus K4 U5 is equal to 0. We can have equation for node 5, and on node 5 we have F4 minus P is equal to 0, and we know that F4 is K4 into U5 minus U4 is equal to P. So we simplify it, that will be minus K4 U4 plus K4 U5 is equal to P. So we have these 5 equations for the 5 nodes. Now it's time to assemble these equations and write them in the form of a matrix. So we will directly write it in the form of a matrix. Right? We will have a 5 by 5 matrix, right? That will be like this, and we have this stiffness matrix, then we will have this deformation matrix, and we will put it equal to the force matrix, right? So this is the U1, U2, U3, U4, and U5, and minus R1, 0, 0, 0, and P. So that will be K1, K1, that was K1 U1 minus K1 U2, right? K1 minus K1, right? All 3 values we have 0. Then we have minus K1, K1 plus K2 minus K2, 0 and 0 in front of it. And we have 0 and minus K2, K2 plus K3 minus K3 and 0. Then we have 0, 0 minus K3, K3 plus K4 and minus K4, and we have 0, 0, 0 minus K4 and K5. So this is how we assemble these equations. Now time to apply the boundary conditions, and we know what are the boundary conditions from this problem. We have U1 equals to 0 and P is equal to the value, I think it's 500 in this question. So we will look at it later on when we go into the solution phase. Let's apply the first boundary condition, that is U1 is equal to 0. We will apply the boundary condition the same way that we applied in the last. So we will make it 1, make it 1, all other we will make it 0, right? So it's 1, 0, 0, 0. So 1 multiplied by U1 will be equal to, make it equal to 0. This doesn't mean that the reaction force has become 0. This doesn't mean that the K1 becomes equals to 1. K1 has become equal to 0. We have just replace the first equation with our boundary condition. We have replaced it with our boundary condition. Now we will multiply this first column with 0, that will be 0. So we can reduce the first column and the first row. It will be a 4 by 4 matrix. K1 plus K2 minus K2 0 0. So minus K2 plus K3 minus K3 0. We have my 0 here for minus K3 plus K4 minus K4. We have 0 0 minus K4 and K5, and we will multiply it with U2, U3, U4 and U5, and that will be equal to 0 0 0 and P. Now comes the solution phase. We will check the values. What are the values? In this problem, it is different than the previous problem. For example, this problem and this was the previous problem, right? In this problem, it was very simple problem because we have these rectangles, but it's a little complex problem. In this element, the shape of an element is a little different, so it is difficult to find the cross-sectional area of this. So we will apply interpolation to find the cross-sectional area of this type of element, right? Okay, now let me give you the values of the problem. So once we have this matrix, we will go to the solution phase. So in this problem, what we are going to do is for example, we have this problem. We divided this problem into 5 elements and 4 elements. Sorry, these are the 4 elements, right? We know this, and the problem is given that this is, let it be W1, and its value is given in the problem, that is 2 inch, right? There is W2, the width from here to here, right? That is W2, that is 1 inch. The total length L of the section, this beam maybe, is 10 inch, right? Okay, then we have the other values, that is the thickness, that is 0.125 inch. We have the value of E, which is 10.4 into 10 raised to power 6 psi. We have load, that is 1000 pound applied at this position downwards. Okay, now unlike the previous problem, it's a little complicated because we don't know we know this width, right? But we don't know this width. We don't know this width, which is the average width of element number 1. We don't know this average width of element number 1. Right? If we got to manage to find this average width of element number 1, we will multiply this average width, let it be WO, this average width with the thickness, right, T, and we will able to get the area of this shape, right? We have this shape of element number 1. So the problem is to find this average thickness, average width of this average width, right? In the previous problem, we have a rectangle shape, so that was easy to find the area of this rectangle, right? Because we have the same average width in the center. Okay, so in this, what we will do the interpolation of this problem to find the so how we will do the interpolation. For example, let it be the final width and let it be the initial width FWI, and this is the WO, which is the required width. Okay, we will apply the interpolation with WF, right, minus WI over the required WO minus WI, right? Because it's area, so we will multiply this width into the thickness, right? They can be cancelled out, so it should not be a problem for you. So we can relate it this direction, length in this direction, we can relate the length in this direction. So that will be equal to L minus 0 over y minus 0. And what is y? Y is the value in the y direction where you want to find the thickness WO. अगर आप यहाँ पे find करना चाहते हैं WO, then the y will be this, right? And you can vary the y and any put any value of y according to where you want to find WO. So by simplifying it, we get an equation which is so this is W naught into T is equal to Wi plus Wf minus Wi into y over L into the thickness, right? So this, what is this W naught T? This is the area. This is the required area at the value of y. So we'll put y. This is the required area, right? So that is Wi plus Wf minus Wi into y over L into T. So I'll put the values. For example, if I put the value of y equals to 0, then it should be 2 inch, right? For example, this was Wi plus Wf minus Wi. So it is equal to W2 plus W1 minus W2 into y over L into T. So just for testing, if we put the value of y equals to 0, right, then we will have this. If we put y equals to 0, right, so we will have this. Okay, let it be W1 and this is W2 minus W1, right? So we put y equals to 0, then this will be W1 and this whole term will become 0 into T, right? So at y equals to 0, we have W1 into T, that is the area A1 at y equals to 0. So now we want to find the areas in between this. For example, this is 2.5. We want to find the area of 2.5 over 2, where we have the value of y equals to 2.5 over 2, right? That will be the average area of element number 1. So the average area of element 1 will be, so we have this W1, that is 1 inch plus 2 minus 1 into 1.25 over 10 into this 0.125, that is the thickness. So from here we will able to get the average area of the element number 1. So let me give you the value of that. So average area of element number 1 is 0.25 inch square. Similarly, we will be able to get the average area of element number 2, element number 3, 4, and 5, and so on. So that will be 0.218 inch square. Average area for element number 3 is 0.1875 inch square. Average area for element number 4 is 0.1562, and average area for element number 5 is 0.125. These are the inch square. So once we have get the areas, we will be able to find the stiffness constant for the element. For example, element number 1, we have average area of element number 1. Let it be average area for element number 1 into EA over L. You remember that. So from here we can get the value of K1, K2, K3, K4 and K5. We will put it in the equations. So what are the values we get? We will put them into the equations. So we get the value of that is 975, right, pound per inch. Similarly, K2 we get the value of K2 that is 845 pound per inch. We will put these values in the matrix we found in the last step. Plus 845 minus 845, 0 and 0. And we have minus 845. We have 1560. We added them. Minus 715, 0, minus 715. We have 1300. Then we have minus 585 and 0, 0, minus 585 and 585. So we will multiply it with U2, U3, U4 and U5 to get the value. So there is 0, 0, 0 and 1000. So from here we can get the values of U2, U3, U4 and U4 by solving it in Excel. We'll get the values of, so what will be the values of U2, U3, U4 and U5 is equal to 0.001026, 0.002210, 0.003608 and 0.005317 inch. So this is the end of the solution phase. Then we will do the post-processing phase, in which we will be able to find the stresses E delta U over L for each element. For element number 1, that will be E U2 minus U1 over L. So this is how we will get the stresses.